So in this video, I'm going to go over systems of particles, but specifically systems of particles within solids. So these are systems of particles. And specifically solids. And I'm going to be interested in rotation. What exactly happens when solids rotate? So we have to define exactly what a solid is. So imagine we have a system of particles again. And what exactly do we mean when we say there is a solid object? So here is a system of particles. There is a coordinate system, and we can point to the ith particle by the position vector Ri. We know that particle Ri has a mass Mi. So I won't put the, actually let's put the mass Mi in there. Okay, so what exactly do we mean when I say that we have a solid object? And the first thing I'm going to say is that when I mean a solid object, I mean that the distance between every object, between every particle, right, is fixed and it doesn't change. So which means that if I take a vector Ri, j to mean the vector Ri minus Rj, so if I have Ri particle and there's an Rj particle right over here, then this vector drawn from j to I, so this is Rj, so in this case, so this vector, right, is called Ri minus Rj. So this vector that points in that direction. So I mean that the distance Rij, or the magnitude of Rij, is some constant, meaning it doesn't change in time. So it is a constant in time. So every particle distance, right, to every other particle, right? There's other better definitions than this, but at least it'll give us a definition of a solid. So Rij, the distance between particles, even if the system is rotated and moved and scaled, all we know is that the Rij distance, right, is not a function of time. Maybe I should do it this way. So this is not a function. Actually, no, maybe it's better to say it's just basically a constant that's based on I and j. So the distance, right? So the distance between R1 and R3, whatever it is, it might be 3 meters, 2 meters, 3 nanometers, 3 femtometers, whatever it is, right, is always a constant. And if it is, right, then we say it's a solid object. So a solid object basically makes sure that every particle distance to every other particle distance is always fixed. And that's what we mean by a solid object. So once we have this definition, right, let's go and take a look exactly what happens when an object is rotated. So imagine that I have a rotation, and specifically, let me erase this portion so that we know it's a solid object. So let's erase this over here. So imagine that this is my coordinate system. So I'm not worried about the coordinate system, but imagine the following. I have an axis, and this is going to be called the rotational axis. And this object is rotating around the rotational axis. So my coordinate system, right, the points in the particle, right, they're going to move. But basically this object is going to basically rotate around the system. So for example, if this is my rotational axis and it's my marker, this marker is going to rotate. Actually, let's make myself as the axis, and I have an object like the marker, and if it's rotating like this in space. So we can imagine that it's rotating, and I don't want to unwind myself from the wire. Okay, so if it's rotating, right, let's find the distance, right? So I'd like to ask myself, number one, what is the kinetic energy associated with this rotation around this axis of motion? And to do this, right, I'm going to say that the kinetic energy of this object rotating around this axis is going to be related to basically the distance to the axis. So this each particle, right, has a perpendicular distance, right, and this segment here. So for example, here's Rj, so this is the mass of the jth particle, and this distance over here, I'm going to give it a label. Let's label this as R double prime, because I already used R prime. R prime was the center of mass frame of reference, so I'm going to use R double prime to mean the vector drawn that's perpendicular to this axis. And actually, I really care what the distance is, so, but it doesn't really matter. So I'm going to take this vector that points to the jth particle. So the distance from the axis for the jth particle. So R double prime arrow I is the distance. It's a vector drawn from the axis to the ith particle. So it's always perpendicular. So what is the magnitude of this distance? It's just, the magnitude of the distance is just without the arrow. So the distance, so let's just make sure you understand. This is Rj is the distance from rotational axis to the jth particle. So this is the rotational axis to the jth particle. So now this jth particle, right? Let me take a look at what it looks like on the top view. So all these particles, right? So if I could look at this from the top view down, we'd have a system of particles that's rotating around this. So if I took a top view of this, this would be the rotational axis. Here's the rotational axis. I'm looking down from the system, and we'll have a bunch of particles right over here, and they're all going to be rotating in a big circle like this. And I know that the distance to the jth particle here to the central axis, right, is given by, so I should have used the j, but here is the double prime. So R double prime j is the distance to that particle. So the question is, how fast is this object rotating around this particle? Is it rotating around this central system? I'm actually going to make an assumption of a couple of things, but the most important being that this object is rotating. Anyway, let's take a look at it anyway. So if I take at this distance, right, I know that after, let's assume that this object is rotating at a constant angular frequency. So the rate of change. We know that if we draw a circle, right, that the arc length s, right, is related to the radius by just saying r theta. So if I look at a small differential in s, right, we know that d differential, if the radius is not changing, right, this would be corresponding to d theta. And if I divide by t on both sides, we get that the tangential speed of the object, v, is equal to r, and d theta is going to be the angular frequency. So I hope you kind of remember your ideas of circular motion, okay? So I'm going to use this, right, to actually try to calculate the total kinetic energy of the system. So I know the kinetic energy of the system, T, right, relative to this axis is going to be given by the sum of all 1/2 mi times the velocity, and I'll actually, let's use velocity, of the ith particle squared. And I'm going to use a double prime to represent the distance, right, the velocity of the particle in my rotating frame of reference. So I shouldn't say it that way, relative to the axis. So there is a velocity of the jth particle, or the ith particle if you want. And it's double prime. I'm going to call it double prime. I'd use double prime over here. So I want this rotational velocity. So I wanted to say something about this rotation. And so if we do that, right, we notice that v double prime I is equal to the rotation vector r double prime at I times omega, if the whole thing is rotating at the same angular frequency, omega. So I'm just basically plugging it into here. The velocity is related to the distance from the axis, where omega is the rotation that this whole system is rotating by. So if I know this, right, I'm also going to make an assumption that, I kind of made an assumption that when I said there was a rotational axis and this object was rotating like this, I should have done something else. I should have said that this object is always pointing in a certain direction, it doesn't change. So it's actually going like this. So when this object is rotating, it's always pointing, but it's always rotating in this direction, where the object is always facing something. So if I do this, right, our kinetic energy term, right, becomes sigma I to n of 1/2 mi. I'm going to plug in this Ri squared, omega squared, because when I plug it into here, it gets squared terms. And the omega squared can come out, and the 1/2 can come out, and we're left with a quantity 1/2 omega squared times summation of I is equal to 1 to n of mi Ri double prime squared. So remember, this is the distance to the axis, and this quantity, right, is an important quantity. Notice it doesn't matter how fast this omega is changing, it's always this quantity. This quantity of mass times the distance to the axis squared, right, for all the particles, is going to be called the moment of inertia. This is called the moment of inertia. And it's usually denoted by the symbol I. I is called the moment of inertia. So we can say that the kinetic energy of this object rotating around this axis, so this object is rotating around this axis, right, is given by a quantity. So we can identify with every mass object, we can identify something called the moment of inertia. So every object you can think of, relative to some axis, I can define something called the moment of inertia I, which is nothing more than the sum of all of the items, each of the mass particles I, and their distance to that axis, the perpendicular distance, which I'm denoting with a double prime I squared, taken from 1 to n. And so the kinetic energy of the system is given by T, around that axis only, is 1/2 I omega squared. So this is only true when we're talking about systems of particles or solids. So if you have a solid object and it's rotating around the axis, and technically I have to make sure that the object is not rotating on itself in a center of mass frame of reference. Okay, so I should be always making sure that there is no center of mass rotation. Remember, every distribution of particles, right? There is a center of mass somewhere in the convex hull of the volume. We'll actually find the center of mass. And the center of mass, right, this object could be rotating on itself like this. I'm going to be assuming that rotation, right, does not exist. And if it does not exist, then the kinetic energy of this object going around an axis is given by 1/2 I omega squared, where I is the moment of inertia. And with this, let's do some calculations for calculating the moment of inertia of some objects and then calculate the kinetic energy associated with that rotation. So let me erase this. So this is an important equation. So moment of inertia is the mass of the object of each particle, the sum of all masses of particles times the distance to the axis. I'm using a double prime. Again, remember, when I use R prime, that means a center of mass frame of reference. So when I'm using R double prime, that's meaning that distance from an axis. Rotational axis. So let me erase this. And let's do some calculations. So this is actually now moments of inertia. So I kind of set up everything so you understand where moments of inertia comes in. So the moment of inertia comes in only for solid objects. So this is called the moment of inertia. So when somebody says a moment of inertia, they're assuming a solid object, because once you have a solid object and you're rotating it around some axis, and I know the moment of inertia, so our moment of inertia is defined to be the sum of all particles, a system of particles from line to n, with mass mi and the distance, so this is ri, of the ith particle to some rotational axis squared. Okay, so once we define this, right, we can actually start doing some calculations on this. If I say, so if I want to do this the continuous case, right, the continuous case would be, so I have some distribution, here's my rotational axis, and if I have a little mass element over here, and it is a distance of r double prime from here to here, then we could actually sum up and say the continuous distribution is my system of particles now are in a distribution in the system, which is now becomes an integral of Ri squared dm. So remember, I'm using double prime to mean the distance from the axis. Okay, so r prime I'm always going to use as center mass frame of reference in these videos. So this is over the volume. So let's do an example of calculating the moment of inertia. So let's do the simplest example of, actually let's do a simple example of a single mass. So if somebody told you that you have a rotational axis and there is a mass m, it's a distance of, let's make it as x, and this is the rotational axis, and this object is rotating like this. So this axis, let's say it's in the plane of the board, and I can't do 3 dimensions properly, but imagine that thing is rotating at a rate of omega. And first, let's calculate the moment of inertia. So the moment of inertia in this case, right, happens to be just the sum of all particles and their distance apart. So this is really, I'll write the equation from 1 to n is 1, right? And this is the mass of the particle and times the distance, r double prime I squared. So in this case, it just happens to be mass times x squared. That's the moment of inertia. So if I wanted to calculate this kinetic energy associated with this object rotating around this axis, and I'm not going to worry about, so this is a point particle, and it's got a mass m, and so if I had to calculate this kinetic energy of the system, right, I'd say that the kinetic energy is T. Remember, I'm using T because, remember, all these equations eventually are trying to build up your understanding of Lagrange equations of motion. So T, so remember Lagrangian I said was T minus V. T is actually the kinetic energy. So the kinetic energy for this case is 1/2 I omega squared. So if this thing is rotating at an angular frequency of omega, then I can say that the total kinetic energy is 1/2 I omega squared. In this case, we can plug it in, it'll just be 1/2 mass times x squared omega squared. And if you kind of remember, right, this x omega, right, is the tangential velocity, and this really does come out to be 1/2 m v squared. So remember, x omega is equal to v. So if I look at the top view, the velocity going this way, well, into the board, right, is basically given by x times the radius, r, times omega. So if you kind of remember that. So it actually is the kinetic energy. But the whole point is, for solid objects, right, we have a strange quantity called the moment of inertia. The strange quantity comes automatically. Later we'll see that this moment of inertia can be extended into something called a tensor. It's called the moment of the inertia moment of inertial tensor, or the inertial tensor, and it's actually going to be a matrix. And we can actually show that later, right, that we'll get a similar equation with a matrix and omega being the rotational angular, how do you say it, the rotational vector associated with this. And I'm not even showing you what omega is, but we can treat omega later, right, to be a vector that is perpendicular to the rotation. So if the rotation like this, omega is going to be pointing perpendicular to this. But let's just understand the basics, right, first, before I start going into this symmetric 3x3 matrix called the moment of inertia tensor. Anyway, so let me erase all of this and let's do another calculation. Let's do a continuous case, and so let's calculate the moment of inertia of, so let's calculate the moment of inertia of a stick. So here's a stick, and it's going to be lying on the x-axis from 0 all the way up to length L, and I'm going to so it's a uniform stick of mass m. So here's my stick, and that extends along the x-axis, and the z-axis is coming towards us actually, but it's okay, it's fine. So once we have this, the rotational axis is the y-axis. So this object, this stick, is basically rotating like this. Like this. Well, hopefully you can understand that. So the question is, what is the moment of inertia? Because remember, the moment of inertia is based relative to some kind of a rotational axis. Our rotational axis is the y-axis. So let's calculate the moment of inertia for that rotational axis. So if we look at it, right, we'll say that the moment of inertia is, and I'm going to take a little mass element, a differential mass element dm. The distance from here to here is x. And so the moment of inertia, right, is going to be the distance squared times dm. Actually, let me write down the original equation that I wrote down and make sure we understand it. So here's the total mass, and we're going to be integrating r double prime squared dm. So it's this distance to the rotational axis. It's a perpendicular distance. So this is r double prime is really x squared dm. And taken from, and I'm going to take x to be, the total mass is going to be integrated from x equals 0 to L, so I'll write that right away. And it's a uniform mass of length L and mass m. So capital M is the total mass of the stick. Okay, and my M looks like something like a zombie, right? Anyway, here's a total mass of stick m. So we're going to calculate this. So to calculate this integral, right, I'm going to divide by dx. I know that, so this is x is equal to 0 to L of x squared dm. And I'm going to divide by dx and multiply by dx. So we're chaining. We're chaining the system, right, with a new variable x, right? A mass is a function of x. It's an implicit assumption, and we're chaining this mass in terms of x. But I know the mass per unit length is uniform, and this uniform means that dm dx, right, is nothing more than mass of the whole system divided by the length of the system. So I can write this and solve this integral as x squared m over L dx, taken from x is equal to 0 to L. So the m over L drops out, and then you'll see that we're taking an integral of x squared, which is 1/3 x cubed. So this will be equal to m over L taken as 1/3 x cubed, taken from x is equal to 0 to L. And so the 0 doesn't matter. The L cubed, but the L cubed gets dropped with L, so you're left with 1/3 mass of the length squared. And this is the moment of inertia of a stick. So this is the moment of inertia of a stick. Okay, so let's do another example so we can actually feel comfortable. Remember, if all the mass is located at point L, it would be ml squared, but all the mass is distributed across from 0 to L, and suddenly instead of having ml squared, having the mass located at L, it's now distributed, and so the moment of inertia is actually smaller. So the basic idea is the further out the mass is from the center of the axis of rotation, the moment of inertia increases. So when the mass is all located at L, then it would be a distance of L squared. So we'd say L squared m, ml squared. but because it's distributed closer, right, from L to 0 along the x-axis to the axis of rotation, then we have a smaller moment of inertia. So the further out a set of masses are from the rotational axis, the higher the moment of inertia is. We can also say the following, that the more massive a system is, right, the moment of inertia increases. Notice if the mass is increasing, right, then the moment of inertia. So the moment of inertia is related to both the mass of a system and also the distance from the rotational axis. Okay, so let's do another example. These are straightforward moment of inertia calculations. So actually one more thing. So I've calculated the moment of inertia. So if somebody asked you, right, so here's my rotational axis, here's a stick, and here's my rotation around the y-axis, here's along my x-axis. I know the moment of inertia is equal to 1/3 mass of L squared. And somebody's asking you, well, what's the kinetic energy associated with the system rotating? Well, then you'd actually say that it is nothing more than the kinetic energy is 1/2 I omega squared. Okay, so in this case, it happens to be equal to 1/2 times 1/3 m L squared times omega squared. So it depends on how fast this angular frequency of rotation is, the rate change of rotation, radians per second. So this is the angular frequency. So we can expand this and it'll get 1/6 mL squared omega squared is the kinetic energy of rotation of the stick going around the y-axis. So okay, so now we know it's something about a stick. So we know the stick has a 1/3 mL squared. So let's try something of a ring. A ring is another common thing that we do for rotations. Actually, there's many actually, let's do the simplest one. Actually, I should have asked you another question before that. It just dawned on me. Yeah, let's do that too. So if I have a rotational stick, here's a stick. If my y-axis is rotating, right, like this, then I know the moment of inertia, right, is equal to 1/3 mL squared. So remember this, I just said this just to make sure. And it's got a mass m, so it's mL squared. But what exactly happens, right, if so this rotational axis, right, let's label this, right, as IY. That's my rotational axis. So if IY is under the rotational axis of this object, right, then this 1/3 mL squared we can calculate. But how about if I take a rotational axis around the z-axis? So here's my x-axis, here's my y-axis, and initially my rotational axis was this way. So this stick was rotating like this. But what exactly happens if I create a perpendicular axis and the stick is now rotating in the plane of the board and my z-axis is coming towards you? So here's my z-axis and it's rotating. Well, in that axis, right, I'll call this IZ because this is my rotational axis, now the z-axis. What would be the rotational moment of inertia for the z-axis? And again, in that axis, you'll see that this is actually symmetrical and it'll be 1/3 mL squared. But how about the rotational axis if the stick was along a thin uniform stick that's along the x-axis, and then I rotate around the x-axis? Would there be any kinetic energy associated with it? And I'll call this rotational axis IX. And you'll see that all of the mass elements are actually at a distance of 0 from the rotational axis. So when I sum up all of the distances squared, dm, so this is really the sum of I to 1 to n of r double prime squared dm along the x-axis, which is really an integral, right? So this is really double prime squared dm. That integral, right, this distance is always 0, and so we have a moment of inertia effectively 0, or very close to it, really. We don't have an infinitely thin stick. Okay, so now that you got the idea, right, we can actually generally we can actually select any rotational axis, and that's our intent. Can we find, if somebody gave you an arbitrary rotational axis, right, would I be able to find out the kinetic energy and also some quantity called angular momentum? And those ideas, right, are a little more advanced, which I'll make some videos to understand, but we're only doing simple axes, so we're not worrying about that. And that leads into comments of like inertial tensors, so that T becomes a 3x3 matrix, a symmetric 3x3 matrix, and that goes into inertial, it's called the moment of inertia, or the inertial tensor. But let's not worry about that. So anyway, I think I slightly went off topic there, just to make sure you understand some things. But now imagine that we have a ring, a thin ring. It's got a radius of r, and the mass is uniformly distributed across this ring. Of course, my graphs are horrible, but that's okay. I expect people to have horrible handwriting, but I really want you guys to actually get the habit of actually drawing little diagrams and solving equations, because that's the purpose of physics. This is modeling. It's not how good of an artist you are, it's basically how good you are at like drawing a model and understanding what's happening in the system. So here is a ring. It's in the plane of this board, and I'm going to take my rotational axis perpendicular to this. I can take any rotational axis, but I'll be looking at a rotational axis that's perpendicular to the plane of the board. So let's assume it's coming towards you. And I'm going to calculate the moment of inertia for this system. So it's a ring. So this is actually a thin ring. And this thin ring, right, has it's got a mass of m, total mass m. And so what we're trying to do is calculate the moment of inertia. The moment of inertia, the rotational axis is coming towards you, so that's a little dot, the arrow coming towards you. And I is equal to the integral of r, the distance to that axis, from squared dm over the total mass, or the volume if you want, whatever the integral is. So, but r double prime, right, the distance is always fixed, so this becomes r squared dm. It just came out as a constant over the mass, and that's equal to just mr squared. So a thin ring of mass m of radius r with the rotational axis perpendicular to that, right, is just given by a moment of inertia given by mr squared. So that was a really nice clean derivation of the moment of inertia. Okay, so now let's extend this idea a little bit further. And so let me erase this. So if somebody asks you what is the, so if this ring is rotating, right, with an angular frequency of omega, what is the kinetic energy? Well, you're going to say it's T is given by 1/2 I omega squared. For this ring, it happens to be mr squared times omega squared. And so we have 1/2 mr squared omega squared is the kinetic energy of the system. So this object is spinning, and it'll have a kinetic energy of mr squared. So the main thing you should learn is that kinetic energy is 1/2 I omega squared, and I depends on the solid object you're rotating. Now remember, this definition of solid is very important. Moment of inertia only makes sense, right, when you look at solids. And these solids, we can define a quantity called r double prime squared. Now, if this is a liquid, right, you have to be a little more careful because a liquid moves and these things change. So this moment of inertia, right, is kind of more difficult because it's changing in time. So the meaning of moment of inertia makes most sense, right, when we look at solid objects. It doesn't make much sense when we start looking at liquids. So I'm specifically looking at solid objects. So anyway, so the moment of inertia of thin ring is I mr squared. So let's extend this, right, to a solid disk. So imagine that we have a disk, and it's got a mass of m, and it's got a radius of r, and the total mass m, and again the rotational axis perpendicular to the thin disk, so it's coming out this way. So if the disk is in the plane of this board, then the perpendicular axis is coming towards you. Okay, and we're going to calculate the moment of inertia of this system. Actually, there's a couple of ways of doing it, but let's just, because this really depends on how comfortable you are feeling like with integrals and double integrals and stuff, but we can actually do it pretty darn quickly. So let's try saying the moment of inertia is really nothing more than dm. This is the definition I'm going to go with over the mass of the system. I know that this is nothing more than, if I take r to be so I'm going to take my differential mass element, and I'm going to say r is the distance of this differential mass element from this axis. So this becomes r squared dm. And r is going to be going from 0 to capital R. Now I'm going to do a chain on this, and I'm going to chain it, right, saying, okay, well, this differential mass element, right, I'm going to divide this into a little circle, a strip of land, right, call this, so this strip of the perimeter of a circle, right, this strip, I'm going to call it as dA, an area element. And this area element, right, which is the perimeter of that circle of radius r, right, will have a length of 2 pi r and a thickness of dr. So I'm going to change this, I'm going to chain this rule into the integral of r squared dm dA times dA. So where here is my circle, so this little strip, right, going from here to here is r, and the distance between these two points, right, is called dr. Actually, maybe I should draw a bigger diagram on this here. So I'm taking my original solid disk, and I'm going to take, so here is my big solid disk, and this is r, this is my dm, and I'm going to call this whole area, right, from here to here, right, as a differential area dA. And I'm going to chain this mass, right, in terms of dAs. So I can divide by dA and multiply by dA. And what is this differential area? Well, if you think about it, differential area is roughly the perimeter of the circle. There's two ways of doing it, and they're both correct. They both give you the same answer. But I'm actually going to assume that it's 2 pi r, and the thickness is dr. From here to here is dr. The differential from the thickness is dr. So this would be 2 pi r, the perimeter, times dr. That's the strip of perimeter space, right, around that ring. And so I can substitute this into this equation. So let me erase this. You can always rewind it, right? Rewind this. So r squared, what is dm? Mass per unit area? Well, I know the mass per unit area in this region is supposed to be uniform, so I'm going to assume it's a uniform disk that's spread with a radius of pi r squared. I know what that is. It's the mass divisible by pi r squared. And the area is really 2 pi r dr. Okay? So we can now drop the pi's. The r squared can come out. So this is taken from 0 to capital R, right? So this is the mass of the object, and there's a 2 coming out. And now we have an integral of, and there's an r squared. Let's not forget the r squared. Then there's an integral of r cubed dr taken from 0 to r. And so this is 2m over r squared. The integral of r is r cubed is r to the 4th 1/4. So this is really 1/4 r to the 4th taken in the limits taken from r taken from 0 to r. In this case, you can see the 2 drops away 2, so we're getting r to the 4th, r squared, so we're getting 1/2 m r squared. So the moment of inertia of a solid disk is calculated to be nothing more than 1/2 m r squared. Wow, 40 minutes already. Okay, so let's now calculate, let's put some of these objects into action to calculate moments of inertia, right, or more complicated systems. So we calculated the following, and let me summarize. So, well, actually, before I do that, what's the kinetic energy of the system? Well, the kinetic energy of the system is nothing more than 1/2 I omega squared. And so this would be 1/2 times 1/2 m r squared omega squared. So I'm just trying to make sure that you remember that this is an important equation. The whole purpose of calculating this moment of inertia in these examples is so that we can show that the moment of inertia is related to the kinetic energy of the system, the rotational energy of the system. But later we'll actually see that we can use the moment of inertia to calculate something called the angular momentum of the system also. So in these simple cases it doesn't really. So let me erase everything. So let me summarize what we've done so far. What we've done so far is calculated moments of inertia for the following systems. So we've calculated the moment of inertia for the following systems. So for a thin ring, actually a stick, along the x-axis, right, we found that the moment of inertia was given by, actually maybe I should draw a little diagram. Yeah, I think that's probably better. So if I have a stick, and the rotational axis is along the y-axis from 0 to L, and it's got a mass of m, the moment of inertia was given by 1/3 mass L squared. If we had a thin ring of a radius r and a mass m, so here's our thin ring, and the rotational axis is coming out perpendicular, okay, it's perpendicular to the ring. So hopefully you can imagine this is a three-dimensional object. It's coming out of the board if you want. Then the moment of inertia was given by mr squared. And if I have a solid disk, and the rotational axis again is perpendicular and the distance of, sorry, the radius is r, then the moment of inertia is given by 1/2 mr squared. So the further out the mass is from the object, right, like here, the furthest we can do from a circle point, right, is mr squared. But if the mass is distributed in that region, then the moment of inertia is smaller. So I can actually start seeing that why moments of inertia are small. Anyway, 3 equations. But could we use it to construct more complicated systems? And what I'll do is calculate the moment of inertia of, let's imagine that we have, actually let's calculate some moments of inertia just based on our understanding of things. So imagine now that I have a rotational axis and I have a stick, and here's our stick. And it lies on the x-axis and it's got a length of L, but the axis of rotation is around the y-axis. So here's our y-axis, here's the x-axis, and it's got a length of L, so it looks much like this, but the stick is actually centered at the origin. So it goes from minus L over 2 to a positive L over 2. Now we can actually do this calculation 2 ways. One way is we can actually go from definition and build up the moment of inertia of a stick, going from minus L over 2, L over 2. I'll do that first example. But in the second example, I'm going to say, well, look, this stick really is composed of 2 separate sticks, this stick and this stick. And I'll add the moments of inertia to both, right, to get the full moment of inertia. Both will give us the same answer. So let's start from minus L over 2 to positive L over 2. So if that's true, right, from definition, we know that, so take a differential mass element, dm, it's located, so we're assuming the total mass of the stick is m and the total length of the stick is L. So much like, exactly like here, 1/3 ml squared. And if you have a rough idea what's going to happen, notice that the mass, right, is distributed closer to the axis. So whatever moment of inertia I'm going to get, it's going to be smaller than 1/3 ml squared. It's going to be smaller. But let's do the calculation directly from definition. So directly from definition means that I can calculate the moment of inertia to be the integral of, I'm using double prime to remember it's the distance from the axis, squared dm, taken from x is equal to minus L over 2 to L over 2. But this differential mass element, right, is at a distance of x along the axis. So remember, the rotation is around the y-axis, like this. So the stick is like rotating in every, along perpendicular to the y-axis. So this is really the integral of x is equal to minus L over 2 to L over 2 of x squared and dm. Next, I'm going to do a chain. Actually, is there space on the board? Yeah, I can do this. I can chain it, right, with divided by, basically, actually, let me just do it. I'm chaining this, right, using a chain rule, dx, dx. Okay, so what is the mass per unit length? Well, that's m over L, so this is really the integral of x taken from minus L over 2 to L over 2 of x squared dm. Because it's a uniform stick, that's just the mass over the whole stick length, and dx. So we can pull out m over L and then integrate x squared, so that'll be 1/3 x cubed, taken from x is equal to minus L over 2 all the way up to L over 2. Okay, so if you think about it very carefully, right, you'll see that the minus x cubed, I can pull out the 3, so maybe I'll do it right now so I can just worry about it outside. And then we're taking L over 2 minus L over 2, but L over 2 minus cubed is actually a minus, and so we're getting a 2L over 2 cubed. So this is really m over 3L, and we're going to substitute L over 2 cubed minus L over 2 cubed, which becomes 2. So this is the answer. So the moment of inertia for this system I, can you see it on the board? I hope so. So the moment of inertia I is given by, let's see, there's a 2 over 3, okay, so that's 8, and there's a 2 on top, and 3, 24. 2 over 24 is 1/12, so I'm getting 1 over 12 m times L squared, because it's L cubed divided by L is L squared. So this is the moment of inertia for this stick. So we've calculated the moment of inertia of a stick that's along the x-axis. So here's our rotational axis, like this. From this is minus L over 2 to, positive L over 2 to minus L over 2, and we calculated the moment of inertia to be 1/12 ml squared. Notice I expected it to be smaller than ml squared, and it is. 1/12 is smaller than 1/3. Okay, great. But is there another way of doing it? Yeah. We can say that this stick, right, instead of going from definition, right, we can actually say it's composed of 2 sticks. So the moment of inertia is equal to, actually I can say this portion of the stick, let's call it S1 plus S2, and we're same integral, right? But this is independent of this. It's just 2 different regions of integration, and so this really integral, right, is really S1 r double prime squared dm plus the integral of S2 r double prime squared dm. And what is this? This is definition of I stick 1 and plus the inertia of stick number 2. So we can do that calculation. Let's do that. So instead of actually doing these integrals, let's calculate the moment of inertia of this stick piece. So we took a large stick and said it's actually composed of 2 half sticks. So this stick and this stack, which is like half the length. So how do we calculate the moment of inertia of each of the pieces? Let's go through that. Let's go. So if this was half a stick, right, its length is L over 2, and I can use this formula. So that formula says it's 1/3 the mass. What's the mass of this whole system? Well, it's m over 2, so the mass is now m over 2. And L squared, right, is really L over 2 squared. So this is the moment of inertia of this object. What's the moment of inertia of this object? Well, it doesn't really matter whether you selected this object. They're both identical, and you're only looking at the distances from this object. So we're going to see this moment of inertia appear again. It's the same equation plus 1/3. What's the mass of this portion of the stick? It's mass divided by 2. And what is the length of the stick? It's L over 2 squared. So again, we're going to see this 1/3. So 1/3, let's do the calculation. So this is 2 squared is 4. 4 times 2 is 8. 8 times 3 is 1/24th. ml squared plus, and again it'll get 1/24th ml squared. And together we'll get 1 over 12 ml squared. That's the moment of inertia. So what we've done is calculated by construction, right, of things I know, in this case the stick, and I've constructed the moment of inertia of a stick that's off-center. Later we'll actually see, I'll do another video of something called the parallel axis theorem, where we can actually take the moment of inertia around an axis that's parallel to the original. Okay, so, but I'll have to take the axis to be somewhere around the center of mass, and so I'll give you something else called the parallel axis theorem, which I don't think I have time to discuss in class, but I will do it as a video so you can actually watch and understand what's happening. Okay, anyway, so I've calculated this stick. Now let's do another example of calculating something more complicated. Imagine the following. We have a wheel. So here's the flywheel. It consists of a thin ring of mass m, and let's assume it's got a radius of r. So it's got a mass of m, and let's call it mr. I think that's what I used in the lecture. I think I used mr. And it's got a radius of r. Okay, actually let's use capital R for the ring. Okay. And this ring, we already know what the moment of inertia around an axis perpendicular to this. We already know it's going to be mr squared. We know that. But instead, let's also assume that there is, so this is the mass of the ring. Let's assume that there's spokes. And these spokes are uniform sticks. And there's 4 of them. So the 4 spokes are basically, so this thing is rotating this way, and well, it doesn't really matter about the rotation, right? It's just, we're going to calculate the moment of inertia. So the moment of inertia, basically, I'm going to assume the axis is perpendicular. I'm going to assume that the mass of each stick, let's call it ms. And I'd like to calculate the moment of inertia of this system. Okay, so let's ask ourselves, okay, well, what is the total moment of inertia? Well, it's going to be the moment of inertia of this ring. Actually, if you're wondering, right, as a physicist, right, I would actually say this is the integral of r double prime squared dm, okay? And I'm going to say that I'm going to take a look at, so I'm going to call ms1, right, to be the mass of this stick, and then the mass of the second stick is ms2, and so on, all the way around. So I'm going to say that a lot of times when you do these calculations, writing this, right, is kind of really strenuous. I know it's only a couple of characters, but you really want to say you're integrating m over the mass of the ring and ms1 plus ms2 plus ms3. So sometimes we don't really care about the integrand. We really want to say that it's really the sum of 4 integrals, and so sometimes we leave it out and just write this arbitrarily as the moment of inertia is really something, which we leave blank and say something, and that's equal to the integral of m ring plus the integral of ms1 plus the integral ms2 plus the integral of ms3. So again, this is a contracted notation, right? So you really want to say that you're actually, the integrand is the same. So if you're kind of curious, right, how I can do things like this, right, it's just a notational convenience that we can do things like this. So we don't waste time writing the integrand, 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 repeat it. So back to the original integral. So we want to say that's really the integral of this. So let's go back to our problem. I want to find the moment of inertia of this thing, and the axis perpendicular to this. So the first one is the moment of inertia of the let me write it over here because I want to use this nice leftover space, right, to write the answer. So this is the moment of inertia for the outside ring, MR. And then we got to integrate from ms1, this stick length, and then another stick length, ms2, and then ms3, and then ms4. Wow, that's a lot of writing. But so let's calculate it. So the outer ring, right, has a moment of inertia of, if we look at it, this mr squared. So this is m, the mass of this outer ring, times r squared. And we have 4 of these identical sticks, right? And actually, maybe let's call them identical because this is too painful to actually do. So write this over and over again. So this mr squared, and what is the moment of inertia of a stick that's rotating over here? Well, we have a formula for a stick that's exactly here, and it's proportional to the lengths, but I have to use, so there's 4 of these, so 4 times 1/3 the mass of the sticks times the length of the stick, and the length of the stick happens to be r, and squared. And so we can factor things out and say that the total moment of inertia, right, is r squared factored out. So we have mr plus 4/3 ms times r squared is the moment of inertia of this system. You can extend these ideas, right, with other systems. So like we could assume that there is maybe there's a, actually, yeah, let's just, I think you got the general idea of adding this, okay? So you can take things that we know and use them to compose more complicated objects. So this is the moment of inertia. Yeah, I think it's that should be enough for this video. And once you've understood moments of inertia, right, we're actually going to incorporate it into Lagrange equations of motion, and I'll make videos for that. So the next set of videos, the next video after this, I'll be doing it directly right after this. So I'll be talking about some examples of using Lagrange. And so now you have a rough idea. Once you calculate a moment of inertia, we can say the kinetic energy T is 1/2 I omega squared. And that's what I want you to learn in this video. So that once you calculate the moment of inertia, and I have an axis, and once I wanted to calculate the kinetic energy of the system, it's 1/2 I omega squared. And later, not right now, but later, I don't need it, but angular momentum, right, is given by I omega. We're actually going to see that later. Long video.